Okay, anybody have any questions from last time? Okay, I want to introduce, so remember last time I talked about this idea where we have directional and non-directional quantities. And the non-directional ones tend to be the ones that we're more familiar with using. The directional ones are the ones that we want for physics because they have more information in them. And so I said position is directional. They're not really equivalent to position non-directionally. But then I said the next one is displacement, D. That does have direction information. And the non-directional equivalent to that we're used to is distance. And then there were some more, and we'll get to those. But this is what we're on right now. The relationship between displacement and distance, how you calculate each one of those. So displacement and distance. Yes? Previous. And also we're not doing the quiz today. Okay. I know. I sent it, yeah. But I do want to say, so for the, I decided that at the last minute, which I think people sort of sometimes like are annoyed about when I do that, but because you study for it or whatever and then you don't have it. But for me, for my purposes, like I'm trying to get you to study this stuff in a certain order, in a certain amount here and there, you know. And so like to me, if you study for a quiz and we don't have it, like it's still getting you to the point that I'm, you know what I mean? Like it's still serving a purpose. So anyways, you didn't ask that or say that, but you know, there's no such thing as wasted studying, you know what I mean? Although there is studying that keeps you from studying in other classes, I suppose, but yeah. Okay, no, that quiz is gone. So the first quiz that we're going to do is the next one scheduled on the syllabus. And then our total quiz score is just going to be divided among one fewer quizzes. Yep. Okay, so consider two instants, T1, we'll call that the earlier one, and T2, that's the later instant. Then the displacement from T1 to T2 displacement from T1 to T2 is D, and it's equal to the position at the later instant minus the position at the earlier instant. So in words, you know, position at the later instant minus the position at the earlier instant. And one thing to notice about this, I'm going to do an example right after this where we'll see how this works, but notice the sign gives the overall direction moved between T1 and T2. Okay, so if you have a positive displacement, it means overall from T1, from the first instant to the later instant, you've moved in the positive direction. If the displacement is negative, it means overall you've moved in the negative direction. So when I say displacement is a directional quantity, that's what I mean. The sign tells you the direction you've gone. Distance doesn't have that, you know. If you go to Iowa, drive to the border, the distance that you've traveled is 100 miles. If you drive from the border of Iowa to here, the distance you've traveled is 100 miles. You lose that directional information. Okay? With displacement, one would be positive and one would be negative. And I'll show you how to do I'll show you how to calculate distance traveled in this example too. Okay, so let's say there's a cliff. Bungee jump off cliffs? That sounds like a terrible idea. Let's make it safer. Okay, so there's like a beam. Still doesn't sound like that great an idea. There's you. New bathing suit. And over here, there's some landmarks. So here's the top of a cliff. And then here's the water down below. Don't forget to put the bungee on. Okay. So bungee jumper. Oh, we need one more little. Let's say right here, there's a bird's nest. So bungee jumper in 2 seconds, he touches the water. It's not really ideal in bungee jumping, but it just makes me have to draw less landmarks. But he just touches it. He doesn't hurt himself. In 2 more seconds, he reaches the height of the lower cliff. Call that point A. And finally, in 2 more seconds, he reaches the height of the nest. So first, let's do what we did before, draw a position versus time graph of the motion. And then second, what's the displacement from the start of this motion to the end? We need all that stuff. Yeah, we do. So let's choose the 0 to be the 0 position is at the water. We do need to know some distances. I'll give that too. Yep. So we'll choose the 0 position at the water. Positive direction up. The 0 time we'll make at the start of the motion. And then as far as the distances, let's say, this is 2 meters. And let's say this is 5 meters. And this is 3 meters. Okay, well, first I'm going to sketch out that kind of number liney thing that lets us show what the path is. So here's the top. Here's that point A. Here's the nest. And here's the water. And the path goes like this. The person jumps down and gets to the water, then bounces back up and gets to the point A, and then goes back down to the nest. I don't know what I would call this. Just it's a way to just sort of visualize the motion. You know, it's like a picture of the motion itself, kind of. Yeah, the path. Okay, and what's the next step that we did last time? First, let's label. Yep, we'll label the locations of these things. So we know that this is our 0 down at the water, and our positive direction is up. The distance between the water and the nest is 3 meters. So if you go 3 meters in the positive direction from 0, what's the label at the nest? Yep, +3. And then it's 5 meters from the nest to A. So what's the label at A? +8. And then it's 2 more meters to the top. So what's that? +10. Perfect. And then we know that from here to here takes 2 seconds. Our 0 time was right when it started. So what's the time here? 2. So yeah, this is 0. Down at the bottom is 2 seconds. Then 2 more seconds to get to A. So what's the time label here? 4. And what's the time label back at the nest? 6. So now we have everything laid out so we can do the table. At 0 time, we're at position positive 10. At time 2 seconds, we're at position 0. At time 4 seconds, we're at position 8 meters. And then at time 6 seconds, we're at position 3 meters. And now we can plot those points. So we always have time here and position here. The times that matter are 0, 2, 4, 6. And the positions that matter are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 10. This is 5. This is 3. This is 8. So the points are 0, 10. 2, 0. 4, 8. And 6, 3. And like I said before, if you want to just draw straight lines between them, that's fine with me. It would be some kind of shape like this if you knew everything going on in between. But we're not given that much information. Okay, so that's the answer to part A. But now we want the displacement. No, but I asked for that. So you need it for A. Okay, so displacement now. We want the displacement from the start to the end of the motion. The easiest way to get that is from this table that I wrote. So we want the displacement is the position at the end, the position at 6, minus the position at 0. So the position at 6 is 3 meters. The position at 0 is 10 meters. And so the displacement is negative 7 meters. Okay, so what that's saying is the person starts here and ends here. The distance between those two is 7 meters. And since the positive direction is this way, the net motion of the person over that time is in the negative downward direction. Okay. So there's 2 bits of information. There's the distance between those 2 points. That's the absolute value. That's the 7. And then there's the negative sign saying that's the direction you move. Yep.
So can we use displacement and net direction interchangeably or not?
Displacement has 2 pieces of information. One is like a total distance between the 2 points, and the other one is the direction. So displacement actually has more information than just the direction, but it does have that too. Yep.
So for our displacement equation we put at the top, so is it more like final time minus initial as opposed to?
Well, it doesn't have to be final and starting. You could also do the displacement between the times 4 seconds and 2 seconds, and then you'd use the positions of those two. So it is just a later. If it's not specified, then they're usually trying to imply beginning and end. You're right about that. Yep. They're always implying final and end, I think. But I'll try to be specific about what to instance. Okay, so that's the total displacement between the beginning and the end. And the absolute value of the displacement is the total distance between those 2 points. But that's not the same thing as the total distance that the person traveled. Okay. So let's calculate the total distance that the person traveled. So make a new part C. So the total distance traveled from time equals 0 to 6 seconds. I think the easiest way to do that is to go back to this little, this picture of the path that the person traveled. And each leg has a distance. But with distance, it's always positive, so we're just going to add those up. We're not going to worry about direction at all. So this first path, what's the distance from here to here? 10. The second path, what's the distance from here to here? And then what's the distance from here to here? 5. So we just have 10 plus 8 plus 5, 23. So just add up the lengths of, I'm going to call them the legs, like the legs of the journey. So we add, so distance is equal to 10 plus 8 plus 5 is 23 meters. I don't think so, because it's not something we use in physics, you know, it's just something you use in everyday speech. Like, oh man, like how, you know, if you ran the 3,200 meters in high school track, the distance you ran was 3,200 meters. The displacement you ran was 0. Makes it feel pretty worthless, you know, because you ended right where you started. And so the position at the beginning is the same as the position at the end, and the displacement 0. No, because you definitely know you ran farther than 0. Oh, I see. Well, right. I think what we're hitting is kind of like distance is part of our sort of imprecise like language, and we're trying to put sort of like precise mathematical things, you know. So if you really wanted to be careful about it, yeah, you would make a distinction between the total distance traveled versus the distance from your 2 endpoints. You know, the distance from the 2 endpoints is the absolute value of the displacement. Yeah, but the total distance traveled is more like taking the lengths of those legs and adding them up. Yeah. Any other questions about that? Displacement and distance? So, like I said, in physics, we're not going to use distance. I'm just sort of giving these relationships because distance is something that you are used to talking about and thinking about. So the next thing that we're going to talk about is velocity. And semi-related to that is speed. So remember, if we divide it up into directional quantities and non-directional, position is sort of on its own. Displacement does have direction information, and distance doesn't. You can see that they're very closely related to each other. And now we're on to the next one, where the directional information is velocity. And what it's very closely related to is the speed. And speed doesn't have directional information. So to talk about velocity, and this means that velocity is the one that we're going to care about. So to define velocity, we're going to first talk about average velocity. And then we're going to use the idea of average velocity to define instantaneous velocity. And for the most part, instantaneous velocity is the only one of these two that we care about. So the only reason that we're talking about average velocity to start is because to understand instantaneous velocity, you have to first understand average velocity. So this isn't very useful on its own. As we go forward, we're just going to use the word velocity. We're not even going to differentiate between these two because we're always going to be talking about instantaneous velocity. So average velocity. So let's say we choose two instants. T1 is the earlier one. And T2 is the later one. Then the average velocity from T1 to T2 is, I'm going to write it as lowercase v sub avg for average. And it's equal to the position at the later instant minus the position at the earlier instant divided by the time at the later instant minus the time at the earlier instant. So notice that you can also think of this you can also think of the average velocity as the displacement divided by the elapsed time. The elapsed time is always positive. And the displacement can be positive or negative depending on the net direction that the thing moved. And so average velocity can also be positive or negative. And the sign has to match the sign of the displacement. So again, that average velocity tells you overall what direction you moved over that from the earlier instant to the later. Let's think about what the average velocity means on a position versus time graph. So think, how does the average velocity appear on a position versus time graph? So let me just draw a made-up position versus time graph. T on the horizontal, P on the vertical. And let's say that the object that represents its motion. And let's say that this is T1. That's the earlier instant. And this is T2. And that means that this is the position at T1. I'll call that T1. And this is the position at T2. That's P2. And the average velocity is the slope of this line. And it makes sense if you think of the slope as the rise over the run, because what's the rise from this point to this point? You're going from P1 to P2. So the rise is just P2 minus P1. And that's the numerator of that formula for the average velocity. And the run is just this distance. So that's P2 minus P1. And that's the denominator of the formula. Okay, so you can see on a graph, you can see the average velocity as the slope of that line. And if that slope is counterclockwise from the horizontal, like it is in this picture, then that slope is positive. And if it's horizontal, then the slope is 0. And if it's clockwise from the horizontal, like this, then the slope, that average velocity, is negative. Anybody have any questions about that right now? The units of velocity have to be, well, you can tell what it is from the formula. So what are the units if you subtract 2 positions? What do you get for the units for the numerator of this formula? Meters or whatever units of length you're using. Put in SI units, meters. And what are the units for the denominator? Seconds or any other unit of time. And so you have meters divided by seconds. And so the units for velocity are meters per second. Or the units for velocity have to be length divided by time. And the SI units have to be meters per second. Okay. So now let's talk about instantaneous velocity. So that has to do with your velocity at a single instant. It's, like your speedometer tells you your instantaneous speed. It tells you at that instant how fast you're going. And instantaneous velocity is related to that. So let's say okay, so let's say you choose an instant that's represented by the time t. The instantaneous velocity is approximated by calculating the average velocity for a time t1 that's just less than t, and a time t2 that's just greater than t. Okay, so I'll show you how this works. So for example, let's say that we know that the position given as a function of time is equal to 2t cubed. Okay. So for whatever time you want, if you want to know what the position is when time is equal to 4 seconds, you plug 4 in for t, you cube it, so 64 times 2 is 128, so the position is 128 meters. That's how that works. Let's choose a time t of, I don't know what, 2 seconds. And we want to know what's the instantaneous velocity at that instant. Okay, well, I'm going to do this in a few steps. So step 1, what do you think are some times that are, so what we're going to do is to calculate the instantaneous velocity, we're going to choose 2 times, one that's a little less than that and one that's a little more than that, and we're going to calculate the average velocity. So the first one is I'm going to say my T1 that's a little less than our desired point is going to be 1, and our T2 that's a little more is going to be 3. So T1 is 1 second, and T2 is 3 seconds. Okay. And then we can use those to approximate the velocity, the instantaneous velocity. So let's say the instantaneous velocity is about equal to, well, how do we calculate the formula for the average velocity is the position at the later minus the position at the earlier divided by the elapsed time. So how do we calculate the position at the later? We can just plug it in, yeah. So plug 3 in for t, and you get 27 times 2, so 54. And now we want to do it for 1 second. 1 cubed is 1 times 2 is 2. So the numerator is 54 minus 2. And we're dividing that by the elapsed time, 3 minus 1. And so we get 52 minus 2 is 26 meters per second. Okay, that's our first approximation. But now we're going to do another approximation with those 2 times T1 and T2 closer together. Okay, we're going to see what happens. So T1, let's say this time, our T1 that's slightly less than, so remember the point, all we're trying to come up with is the instantaneous velocity at 2 seconds. But the way we're doing it is trying all these, is taking points on the 2 sides of the function and calculating an average velocity. So now I'm going to pick 2 points that are closer together. Okay. So let's say T1 is equal to 1.9 and T2 is equal to 2.1. Okay, so the velocity, instantaneous velocity approximated by these two is, plug those two things in, you get like 18.5 minus 13.7. I think I need more decimal places actually. Anybody have a calculator? Can you plug those into the... Well, let's just count. Mm-hmm. Okay. 13.718. Okay. And then you have to divide, yeah. And so you divide by 2.1 minus 1.9. And can you divide that one for me too? Point two? 02. 24.02 meters per second. Let's do one more. So step 3, let's choose time 1 equal to 1.99 and time 2 equal to 2.01. Can you calculate those for me again? I'm going to need a lot of decimal places for this. Two, 4, 1, 0, 2. Oh, okay. 2, 0, 2. Okay. Okay. And then divided by 2.01 minus 1.99. Can you calculate that one for me? Zero, 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 two. And if you kept choosing your, so all we started with was one time that we wanted to calculate the instantaneous velocity at. We want the instantaneous velocity at 2 seconds. But to find it, we keep choosing two nearby times and making them closer and closer together. And little by little, we're getting closer and closer to the true instantaneous velocity. And what you'd see if you kept doing this process is what you would kind of probably guess. The true instantaneous velocity is 24 for this function. So little by little, as T1 and T2 pinch closer to T equals 2 seconds, V approaches the instantaneous velocity at T equals 2 seconds. And what it looks like on a position versus time graph So let's say that we have, time on the x-axis, position on the y-axis, and our function looks something like that. And we want to calculate the instantaneous velocity at this point t. So this is p at that point t. The instantaneous velocity is the slope of a line that's tangent to that point. So tangent to the graph at that desired point t. Okay, it's a slope. So this is just a made up one, but is this made up slope that I drew positive or negative? Yep. And if it was up at this point and the slope was like that, it would be zero. That would be zero instantaneous velocity. And if it was like here, the slope is that way, negative. And the sign, well, let me do it like this. So notice there's two things that are important about instantaneous velocity. The first one is that the absolute value of the instantaneous velocity is the instantaneous speed. No, don't stop. Ah!
Is the recording still going?
Mm-hmm. Yeah, you'll get to watch all this on the recording. Hopefully it's going to recover that in a second. Yay! Maybe I should save it. Okay, so oh, it did erase that last bit. So the instantaneous velocity is the slope of the tangent to the position versus time graph at t. Okay. And then the two things to notice The first one is that the absolute value of v instantaneous is the instantaneous speed. Okay, so velocity can be positive or negative. That tells you something about the direction. But if you get rid of the sign and just take the absolute value, it would tell you what the speedometer your car tells you at that instant. Okay, so instantaneous speed is instantaneous velocity without the directional information attached. The second thing to notice is the sign tells the direction that the object is traveling in at that instant. Okay, so in this example, at this instant, is this object traveling in the positive or the negative direction? Positive, because the slope is positive. The sign is positive. If it was at this instant here where the slope is like this, well, I'm exaggerating, but would it be in the positive or negative direction? Negative. So that at that instant, the object would be moving toward, in the negative direction. And if it was right here where the slope is equal to 0, it's not moving in the positive direction. It's not moving in the negative direction. So that's an object that's at rest. It's not moving at all at that instant. Okay. And the last thing I want to say is, yep. If we're thinking about, it can mean any, so we can be talking about any one-dimensional motion or any motion along a line think about. So, and we've just chosen one of, so it could be, say the line is like this, and we chose our positive direction to be that way, then it just means that if the slope is positive, it means it's moving in that direction. If the slope is negative, it's moving in that direction. And if it's 0, it's instantaneously at rest. The absolute value, right, tells you how fast it's moving at that instant, right? Exactly. And the last thing is, I'm not usually going to call it V instantaneous. I'm usually just going to call it V. So whenever I talk about velocity or lowercase v, I mean instantaneous. If I'm ever talking about average velocity, I'll say that specifically. But this is going to be enough. This is going to be so much more important to us than average velocity that I'm just going to call it the velocity. Yep. Yes. Every formula you'll get. Okay, so if you're given an instantaneous velocity of negative 10 meters per second, how would you use that to calculate the instantaneous speed? Just, yeah, exactly. So absolute value gives you the instantaneous speed. If you have the velocity and you want the speed, you just chop the sign and just take the absolute value. Okay. So you can think of velocity as the speed with extra information, extra directional information. Okay, so let's say that you have an object that's moving 15 meters per second in the negative direction. What's v at that instant? So that's a speed. It's moving in the negative direction. So v is equal to, yeah, negative 15, that's right. And then say that an object has a velocity of, negative 30 meters per second. What's the speed? Right. And now we have to talk about acceleration. Yes, please.
Somewhere you should mention that the speed is not the absolute value.
Right. Yes. Mm-hmm.
So there's a question that asks you to find the average velocity.
Yeah. Right. Right. Yeah. Okay, I'll put something on D2L about that. Yes. Yes, thanks. Yeah. So the last quantity we have to talk about, the last directional quantity is acceleration. And if we're talking about directional versus non-directional, we have position, we have displacement, and displacement is related to the non-directional quantity distance. And then we have velocity, and the non-directional quantity speed. And then finally we have acceleration. And in non-directional terms, we think of acceleration as sort of the combination of, like, if the thing's speeding up, we call it acceleration. If it's slowing down, we call it deceleration. We're just going to call everything acceleration here, but we're going to have a sign that associates it with direction. And the way that direction works is not the way that most people would guess off the top of their head. Okay, so just as velocity is a measure of how quickly position is changing. Acceleration is a measure of how quickly velocity is changing. And so you would expect the formula for acceleration would maybe look sort of similar to the form of, to the equation for velocity. You just be replacing position with velocity. And it turns out that's exactly what it is. So acceleration is the velocity at a later instant t2 minus the velocity at an earlier instant t1 divided by the later minus the earlier. It's the form of that equation is exactly the same as the form for average velocity. Average velocity. We are not going to distinguish between average and instantaneous acceleration, although there is a distinction to be made, because in this class, we're only going to deal with constant acceleration when we use these formulas. And so they're the same thing if you have constant acceleration. But yes, you're thinking about it just right. Yep. I don't know, just whatever feels right. Okay, so here's a whole list of things that I want you to notice. The first one is what I just said. For us, there's no distinction between average and instantaneous acceleration. Because we'll only see constant acceleration. Second, you can see this from the equation, if you have a zero acceleration, that means that the velocity isn't changing. Nope, it doesn't mean that, because if the, and if you have a graph of position versus time, the velocity being constant looks like this. Okay, that's what zero acceleration looks like. But if you look at two different times, this time the position is negative, this time the position is positive. It just means it's moving in the same direction without changing its speed. But that speed could be a million miles an hour, you know. Third, in one dimension, which is what we're dealing with right now, a non-zero acceleration can only mean two things. It either means the object is speeding up or slowing down. That's going to change when we get to two dimensions, where something can be moving with a constant speed and still be accelerating. So that's the next thing I'm going to say. How do you know whether an object is speeding up or slowing down and what direction it's going and stuff like that? Well, if the velocity and the acceleration have the same sign, the object is speeding up. And that's true whether they're both positive or both negative. So if they're both positive, the object's moving in the positive direction and speeding up. If they're both negative, the object's moving in the negative direction and speeding up. And if V and A have opposite signs, the object is slowing down. The velocity tells you the direction, and the two signs together tell you whether it's speeding up or slowing down. And I think if you were asked to guess without any extra information, what does it mean for acceleration to be positive or negative? Most people guess positive acceleration means speeding up, negative acceleration means slowing down. But notice that's not how it works. In order to figure out whether something's speeding up or slowing down from the signs, you need to know the sign of the acceleration and the velocity. And it's the way those two relate to each other that determines that. Any questions about that? Okay, go through some examples on whatever day I see you next, Tuesday. We do have lab next week. Okay.